Here we have the first one. A vertical solenoid, a long coil with an iron core, is held in a wooden clamp above a lab bench. The solenoid is connected in series with a battery, a switch S, an ammeter, and a variable resistor. The voltmeter is connected in parallel with the solenoid. Figure 9.1 represents this apparatus. A student closes the switch S and the current in the circuit produces a reading on the ammeter. State what is meant by the current. So the first one is just independent of the circuit. They can ask you independently as well. For 1 mark, we can just write rate of flow of charges back to time only. Part B. The battery consists of 5 1.5 cells in series. So the total EMF would be 5 times 1.5. The reading on the ammeter is 4.0 amperes. And then the size of the state the size of the electromotive force of the battery. Okay, so we calculated the first one already. There are 5 cells in series. Each cell is 1.5 volt. So you gotta multiply 1.5 by the number of cells, and that'll leave you with the answer 7.5 volts. Then you have calculate the total resistance of the series circuit. So what you have here is you need to calculate the total resistance of the circuit. In the circuit, you have 2 components. You have the variable resistor, you have the solenoid. There would be combined resistance, but like I said, the very famous equation of this chapter you use every now and then. For this one, V equals to I times R. Then you rearrange R equals to V divided by I, and the voltage in that case is the total EMF of the battery, because we need to find the total resistance. So we use the total EMF of the battery and we divide it by the total reading of the ammeter. An ammeter in this situation is measuring the total current of the battery. It's connected in series with the components, so it's measuring the total current, and that current would be helpful for us to find the total resistance. So divided by 4.0, and you hit it on the calculator, and what do we get? 4.0. Yep, so we get 1.875 amperes. Sorry, ohm. 875 ohm or volt per ampere, and you round it off to 2 significant figures because all the raw data is in 2 significant figures, and that'll be 1.9 ohm. Then we have the next part. The reading on the voltmeter is 6.5 volt. Calculate the power dissipated in the solenoid. The reading on the voltmeter is 6.5 volt. Is that the reading of the voltage across the solenoid? If it is, then we can safely use the voltage as 6.5. So let's take a look at the apparatus, and you realize over here this voltmeter is connected across the solenoid in parallel with the solenoid. So it is giving you the voltage across the solenoid, and in order to find the power, you write down the formula P equals to V times I. Like I said, we can rearrange this formula and we can come up with power equals to I squared times R, and also power equals to V squared times divided by R, and also power equals to electrical energy times divided by time. So these are the formulas that we use to find the electrical power. So the voltage was 6.5, 6.5 times the current. The current is same through both the appliances, through the resistor, variable resistor, as well as through the solenoid, because the circuit is a series circuit, and in series circuit current remains the same. So times 4.0. So we hit it on the calculator. 6.5 multiply 4.0, we get 26. And the unit of this one would be volt times ampere. So volt into ampere, we also call it watts. Watts with the capital W. Then we have the next one. The solenoid is made of copper, and the student notices that as the time passes, the solenoid becomes extremely warm. Stay explain the effect of this temperature increase on the ammeter reading. All right, kind of an easy one. There are three quantities that are being related in this one. As the temperature increases, the resistance of the solenoid increases. The resistance of the NOID solenoid increases. And hence the current would decrease. Hence the current decreases. So 1 mark for the effect of temperature and the resistance, and the second mark for the effect of increase in resistance on the current. So moving on to the next part, you would have read the statement. It reads the current in the solenoid magnetizes the iron core so that the lower end of the core is the north pole. So we can write it. We can write north over there. So this is your north pole of the solenoid. This one, the lower one, and the upper one would obviously be the south pole. And what else do we have? On figure 9.1, draw the pattern and indicate the direction of the magnetic field in the region surrounding the iron core. All right, for this one, here you have the next one. A student holds an iron cylinder against the bottom surface of the iron core in the solenoid. When he releases the iron cylinder, it stays in contact with the iron core. Explain why the iron cylinder does not fall. So kind of an easy one. First of all, as the cylinder is in contact, it gets magnetized. By the iron core, which was acting like an electromagnet. So it is magnetized in such a way. So you have the cylinder over here, let's say over here. So the top pole of the cylinder would induce an opposite pole with respect to the iron core. So the upper pole of the cylinder would be the south, and the lower one would be the north. So what we can write here is and this one appears to be related to the circuit breaker or something like that, or the relay. Yeah, the relay. Figure 10.1 shows a relay connected to a cell and a switch. So this whole assembly, this whole setup is collectively called as a relay, and it is controlling, this relay is controlling the external circuit, and the external circuit is over here. If somehow these contacts are closed, the external circuit would be switched on, and if these two contacts are open, the external circuit would be switched off. Now the first thing, when the switch S is closed, the iron core is magnetized. The left side of the iron core is the north pole, as shown in figure 10.1. Okay, we can see that the left side of the iron core is the north pole. The iron armature is connected or attracted to the core. Okay, so this one is attracted to the core, this thing. On figure 10.1, mark the south pole of the iron core. So you doesn't get easier than that. If the left side is the north, the right side would be the south pole. Now, the north pole and the south pole of the iron armature. Over here, we would be having the north pole, because only then it can be attracted towards the iron core. And over here we would be having the south pole, because only then it would be attracted towards the north pole. Now for the second part, so the first one was quite an easy one, 2 marks for literally just marking the directions, which are kind of easy. Then we have the next one. The cell is reversed. State what happens to the poles and to the armature. Now first of all, state what happens to the poles and to the armature. To the poles of what? The iron core. Okay, yeah. So as you reverse the direction of the current, now this one is, let's say this one is negative and this one is positive, the direction of current would be reversed, and the current would be something like this. If this is the positive, this is the negative, and you apply the Fleming's right hand grip rule, and your fingers are pointing towards you like this, and your thumb would be pointing towards the right side. So right side would be the north pole in that situation, but you don't really need to apply the right hand rule, because if you reverse the direction of current, the polarity or the poles would be reversed automatically. So this one would be the north and this one now would be the south, but now the magnetic poles induced on the iron core or the iron armature, sorry, would be in such a way that this one becomes north. Let's just write it in different way so we're able to differentiate. Now you change the direction of the current on the iron core, this one became north. Now for the iron armature, this one would become south, and this one in the second case would become north. So the iron armature would be just attracted. It would be attracted either way. So poles are reversed and armature is attracted, because armature has to induce the opposite poles. Whatever the polarity is on the iron core, the armature would induce the opposite poles with respect to the near pole, and they would be attracted anyway. Armature is attracted. Explain why the core is made of iron and not steel. For this one, once again, you need to recall the uh, differences between soft magnetic and hard magnetic material. Iron being the soft magnetic material can be magnetized and demagnetized easily, and steel, on the other hand, retains the magnetism. So what I can write here is iron is a soft magnetic material, and soon as switch is opened, or soon as the circuit switched off, armature is no longer connected or no longer attached. So for the part 3, explain why the core is made up of iron and not steel. Because iron is a soft magnetic material, it acts as a temporary magnet, and as soon as you switch off the circuit, or as soon as there is no current in the circuit, the armature would no longer be attached. Moving on to the next one, figure 10.2 shows the relay connected in a circuit to a 12-volt battery. The bell is not ringing. And this is the circuit that we have. This is the electric bell. This is the thermistor. And this is this one is the relay. And this is what they're saying is coil, which is having some resistance. This is the 12-volt battery. The first one was to name the component X. This is the component X, and this is thermistor. So once again, thermistor is an electrical component. It is a kind of a resistor, a variable resistor, and its resistance depends on the temperature. Explain why the bell rings when the temperature of the resistance rises. So as the temperature increases, the resistance of the thermistor decreases. Alright, it behaves opposite to the conductor. So temperature increase, the resistance decreases for the thermistor. So as temperature increases, resistance of thermistor decreases, and due to which the current in the circuit increases, and relay switch closes, Yeah, so if I explain it over here, this is the situation that we have. So the question was, once again, what happens, why the bell rings when the temperature of the X increases? So when the temperature of this thing increases, its resistance would be decreased. So less resistance means more current can now flow through the circuit. More current can flow. And due to more current in the circuit, this coil becomes strongly magnetized. And it is magnetized strongly, and it is now able to attract or close the relay switch. And we studied that in this section of relay, that it is a magnetic switch which is controlled by magnetizing a coil. So this coil once magnetized, it closes the switch, which is made up of an iron strip or an iron rod or something which can be attracted towards the coil. And as soon as this switch is closed, the relay switch is closed, this external circuit is completed, and the current can now flow through the bell. If the value of current is not large enough, the coil would be having some magnetic field, but the magnetic field would not be strong enough to close the relay switch. And since the external circuit would remain open, the current cannot flow through the bell, and the bell would never ring in that situation. Then we have the next one. When the resistance of X is 2000, the current in the coil is 1.5 milliamperes. This causes the contacts in the relay to close. The resistance of the bell is 2000. Calculate the potential difference across X. Okay, so this is what we need to find out. Calculate the potential difference across the X. So the resistance of the X is 2000, bell is 200. I can write it down over here. This one has resistance 2000. And this resistance is 200. Resistance of the bell is 200. Okay. Calculate the potential difference across X. For the potential difference across X, what we can do is we can find the potential difference by using once again the standard equation. V equals to I times R. Voltage equals to current times voltage, current times resistance. The current is 1.5 milliampere, so 1.5 into 10 to the power negative 3, or 1.5 divided by 1000. You convert it into amperes first. 1.5 divided by 1000. You simply convert it into amperes first, and then multiply by the resistance of that component, which is the component X, and its resistance is 2000. Then you hit it on the calculator. You'll be left with these 3 zeros would be cancelled out by these 3 zeros, and 1.5 times 2 would be 3 volts. Should be 3 volt. You can just hit it on the calculator as it is. Calculate the potential difference across the coil. So potential difference across the component X is 3. This is 3, and the total that you were supplying from the battery was 12 volts. You get 3 volts across the first component, and the remaining volts would be delivered to the second, across the second component, which is 12 minus 3, so 9 volts. minus 3, that equals to 9 volts. The current in the battery. Now we need to find the total current in the battery. So current in the battery once again refers to the total current. For this one, we need to have the total EMF. We do have the total EMF, which is 12 volt, and we need to find the total resistance as well. So total current equals to total voltage divided by total resistance. Once again, the same formula, V equals to I times R. So total current equals to total voltage divided by total resistance. Now what is the total voltage? The total voltage is 12, and we need to figure out the total resistance first. So the total resistance of the circuit, we have the resistance of the coil. The resistance of the coil was okay. We can find the resistance of the coil first. It's not given directly, so we'll need to find the resistance of the coil first. So what was the voltage across the coil? The voltage across the coil was 12, and over here we had 3. So 12 minus 3, it was 9. R equals to V over I. We need to find resistance of the coil first. The voltage across the coil was 9, and the current in the coil is 1.5 milliampere. 1.5 times 10 raised power negative 3, or 0.0015. Yeah, and now I'll hit it on the calculator. 6,000. So the resistance of the coil is 6,000 ohms. I can write it RC. RC stand for the resistance of the coil. Now what is the total resistance of the circuit? It is a series circuit. This one is the series circuit. So you add up the resistance of the what do you have? Add up this resistance, because these two are connected in series. So the total resistance for the series, for the components connected in series, would be 6,000 plus 2,000. 6,000 plus 2,000, and that will be 8,000. For the components connected in series. So now your circuit looks something like this: 12-volt battery, and you combine the two components which were connected in series, and now the total resistance is 8,000. But then across them you have the bell, whose resistance is 200 ohm. Now these two, 8,000 and 200, these are connected in parallel, so you have to sort it out by the formula of parallel combination of resistors. So the total resistance would be first one in the parallel, for parallel, the first resistor now you have is 8,000, and the second one is 200. So the formula is, the shortcut is product over sum. Divided by sum would be 8,000 and 200. Now you hit it on the calculator, and what do we get? 185. Okay, 195.1. Oh, so in 3SF we'll get 195 ohm. 195 ohm is the total resistance of the whole circuit. Once again, we solve the series circuit first. So 2,000 plus 6,000, it was 8,000. Now 8,000 was connected with a resistance of 200 in parallel, so we solved them by the formula of parallel. The shortcut is product over sum. So the total resistance was 195. So 12 divided by 195, we get 0.062 amperes. Now, this question is a tough ask for 2 marks. I mean, first you need to find resistance of the coil, then you need to add them, then you need to apply formula for the parallel combination, then you need to apply Ohm's law once again, or at least they should have given the resistance of the coil directly. So for 2 marks, looks like a tough ask. Alright, anyway, so here we have the last part. Component X is now removed from the circuit and replaced by a different component Y. The bell now rings when bright light shines on it. State the name of the component. So it is a component whose resistance depends on the intensity of light, and we call it light dependent resistor, aka LDR.